1 and 5.
You know? You're like, is that always gonna happen? It doesn't always happen that way, but it's like smack dab right between a 1 and a 5, right at the 3, and when there's x equal to 3, I'm gonna put right there on the curve at x equal to 3, I'm gonna draw a tangent line. This tangent line should be what? Totally parallel. I'll do my best to make it look like it's parallel. See how their slopes are equal?
Mm-hmm.
But it did happen right between 1 and 3. And sometimes you'll find that. If they went from 0 to 6, you're like, watch it happen at 3. Right? If they went from, what? I'm thinking 7 to 9, you're like, it might occur at x equal to 8. But sometimes it's a fraction. But it has to happen at least what? Once, and it can happen more than once. So I'm going to draw, this is number 7. I'm just going to draw a curve, and I want you to see, if we take the endpoints, how many times you can look at this image and tell me how many times you can tell the slope of the secant would equal the slope of the tangent. Okay? First of all, do you have any questions on this? Cool, I'm going to come back to this and I'm going to change this because Art asked about something called Rolle's theorem. It's just slightly different. We're going to take this and add a couple elements to it, okay? This is number 7. All right. Let me do my best to draw this. Okay. That's good. All right, endpoint, and when this is your A, and that's your B. This is just some other curve, right? And it's number 7. It's actually on the next page, 289. Now, draw a secant between these endpoints. Here it is. Now, isn't this the secant? Secant. Could you tell me, or just ask me, how many times you could get slopes of tangents that would equal those slopes of the secants? Basically, how many tangents along that curve are parallel to that secant? Who sees one? I'll just start drawing them. There's more than one.
2
Where do you see one? I'll put it.
on the first one.
He said on the first column. He said right around here when there's some spot. Right about right there. Is that the only one? Where's the next one? Is there one in here?
Underneath.
Probably about right there. Remember, tangents hit that curve in one spot. And the parallel, is that it? So how many? So that's what I mean. It can happen more than once. It can happen more than once. A lot of times you just get once. Cool. Neat. As long as it's differentiable and it's continuous, right? Crazy thing, you got holes and stuff. No, this game's over. Doesn't automatically have to happen. All right. Now, let me come up with a number. I think I'll use 3. Let's see. I'm going to 12x plus 3x squared. Just make sure. I apologize, I should have checked that problem a little bit more carefully. These were right. Guess where the vertex is of this? It's actually a little bit lower in here. So anyways, this graph actually would have done what? Remember negative b over 2a?
Uh-huh.
So when at 2 it got to its lowest point.
But negative b is positive, right? So that's positive x 12 over 3.
So what's
So
going on at
4.
x equal to 2? X equal to 2, you get 12 plus 5, 17 minus 24, what's that, negative 7?
Uh-huh.
So when at x equal to 2, we got a little bit lower at negative 7. But you know what's neat? What goes on at x equal to 3? We got these right, Owen. This was the point 5 comma 20. This was the point 1 comma negative 4. At 2 it actually reached its vertex, so it was like, yeah. But then at 3 it gets where?
No, vertex should be at 4.
At 3 it's what?
3, 6. It's going to be 6, right? The same as
Try it out, let's see. Now, what's going on at x equal to 3 for that for me?
5 minus 36 plus
5 minus 36
plus 45.
plus 3 times 3 squared is 27.
27, yeah.
What do y'all get?
30, negative 4.
Okay, so, and when you notice at x equal to 3, it's at what?
Negative 4.
Negative 4?
Uh-huh.
Okay. So at 1 it was negative 4. At 2 it got down to what? Negative 7. Then 3 it got back to what? Negative 4. So this graph's really going like this, and then it got up to this, like that. And we found out the answer was x equal to what? 3. Boop. Right there. Does that look parallel to that?
Uh-huh.
Okay. Cool. Now I'm going to change this image, and I'm going to change the question. Ready? So in your notes, make this a 3. Now, I'm not doing like number 1.
Doing number
I'm
1.
doing number 1.
Okay.
Right? I just want to really see this picture. Okay. 1, 2, 3. We're zooming in now, everyone. 4, 5, 6, 7. At 1, it got to negative 4, right? At 2, it got down to negative 7.
Mm-hmm.
And then at 3, because that's the interval, it got back to what value? Negative 4.
4. Yeah.
All right. Here's the curve. But you know what's interesting about this question? We just did mean-value theorem, true? What's interesting about this problem, I want you to apply the mean-value theorem here. And think about the slope of the secant. Look at the slope of the secant. That'd be the slope between the 2 points right there.
1 and 3, yeah.
They're both at negative 4, right? Right there and right there. That would be the secant, right?
Uh-huh.
All right, here's my secant. Yep, this was done on purpose. So you can say, what's the slope of that thing?
0.
0. Everyone agree? Slope of the secant. Why is the slope of the secant 0? Because f of 1, right, takes on the same y value as f of 3. Does everyone agree?
Mm-hmm.
But according to mean value theorem, it still holds. There's got to be a point between x equal to 1 and x equal to 3 such that the slope of the what? The tangent will be equal to the slope of the secant. And I bet you know where it's going to happen. At 2. And what would be that slope? 0, right? You can see it, true? Yeah, okay, that's just an extension of what theorem? Mean value theorem? Yeah. But there's actually a name to it, and it's Rolle's theorem. All right, so what's Rolle's theorem? It starts out like this. You can see it with this problem. Rolle's theorem starts out, you know what? What if f of a equals f of b? Right? And then we use all the same language as the mean value theorem. Same language. What if f of a actually equals f of b? As we can see.
Mm-hmm.
And we use all the same language. Well, we can actually write this a little better, can't we? Because we could say this. Ready? F of b minus f of a over b minus a, right?
Mm-hmm.
What would all that equal?
F prime of C.
Okay. We're going to improve this. What's f prime of c going to have to equal every time?
0.
Because if these two numbers are the same numbers, everyone, look, you're the same as this guy. You're the same. It's almost like I call it f of b minus f. They're the same numbers. This number here will turn into what? 0.
0.
So we can actually make this Rolle's theorem and say, okay, you're always gonna be 0. And there's gonna be some what? There'll be some C value that's between A and B. And it's gonna have to take a slope of what on? 0. But we can only say 0 here as long as what? If f of A equal f of B. But when you agree, you're like, oh yeah, that's just the mean value theorem. True? Hey, yeah, I get it. You get it, yeah. If those two y values are the same, then the slope of the secant will be 0. And then f prime of C would be 0. C would be somewhere between it, it's got to take on that slope of 0. And it has to happen at least once, right? So now think of the sine curve, right? What if they had a sine curve that went like this? And they said, okay, go from here all the way to here, right? And see how these take on the same y values?
Mm-hmm.
You're like, all right, how many times is the slope 0? You're like, here, 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 here. Do you all agree?
Mm-hmm.
How many times is the slope of the secant equal to the slope of the tangent? You're like a bunch of times. True? So we can have more of those. But we have to work out that math. We were just showing that there's going to be some value. But I think you all know, where's it going to occur? If it was from 1 to 3, it'll occur
Between 1 and
x
3.
equal 2. Let's
Yep.
just make sure. So I'll keep my 0 here. And what's the first derivative?
Negative 12
12 plus 6.
6x.
You could put C in here. It's okay if you just leave it what letter? X. If you just don't want to make it a C, and you're solving for x. Well, what value do we get when we solve that? C equals 2. It's nice to see it. Everyone see it? It's just nice to see it. You're like, oh yeah, it's right between. Rolls here. Even when I like to put this on a test, I actually like to draw the curve with the secant there, just to help you remember. You know, you see this image of like some curve going like this, and you got like a secant just going, and I'm like, all right. And you saw my language before about the, you know, find that C value that satisfies the conclusion of the mean value theorem. And you're like, oh yeah, I know what's going on. I gotta find a point that's between these two where the slope is what?
0.
What up here then? Alright. You got it. Mean value theorem. Later on, we're going to do integrals. And there's something called the mean value theorem for integrals. If you want to do the math proof in class, we're going to need that. Alright? We actually have to use that to prove the mean value theorem for antiderivatives, for what we call an integral. We go, what's an integral? We haven't gotten to that yet. But that's a cool theorem. Alright. Let's see what we got here. I'll put that. No one in your notes, you can just put 4.3. Let's tear this function up. Let's start talking about words like where the function's increasing, and where's the function decreasing, and where the function's concave up, and where the function's concave down. All these new terms. Define concavity, right? Make sure everyone understands this whole thing. All right. And we'll work through that problem. Okay, well before we do, let's just look at some things. Everyone a function. Maybe you ask something just goes like that. Where is this function increasing?
Where between
Over here on this side, right? Where the slope of the tangent line is positive, right? Where was this function decreasing? Over here, right? Where the slope of the tangent was negative. So, isn't the slope of tangent line first derivative? Okay, so I guess this is all we have to do. If we get the first derivative, whenever the first derivative is positive, the function should be increasing. Do you agree?
So should there be a set of values?
What's that?
Should there be limited set of values like between?
That's right, we'll have to find them.
Okay.
We will find them, that's very good. And it's going to be based off those max and mins, those critical points we find.
Gotcha.
All right, you got it. But at least we know that. We're like, okay, we understand that when that first derivative is positive, we know for a fact that that function is going to be what? Increasing.
Increasing.
But when the first derivative is negative, that function has to be doing what?
Decreasing.
Decreasing. So far, so good? And he goes, but there might seem limit values to see where this happens, yep. And we will do it through these what? Critical points. We'll get the critical points first, and then we'll start looking at this stuff. We might have to test some points, though, just to see, and when we're saying the words positive and negative, the only way you and I are going to be able to tell if the function's positive or negative is just pick some numbers to plug in there to see if it's what? Positive or negative. We won't be so concerned about the number itself, okay? But we'll see that as we work through a problem like this. All right, so that's what? Increase and decreasing. True? And we'll be able to find those max and mins again. Remember, we find max and mins by taking the first derivative set and equal to what? 0. Solve for x. And those are called the critical points. True? But now, I didn't put some limited what? Let me get this thing off here. I didn't put some limited numbers there. So we're going to look at these relative max and mins. Sound good? Now there's another word that's going to come up. It's called concavity. So, a graph that is concave up, everyone, will be a function that does something like that. Hey, doesn't that look like a cup?
Mm-hmm.
So I, on purpose, misspelled concave up. I spelled it what? Cup. Or you can do C what? You pick cup. Okay, like a cup. So when the graph's doing something like this, it's going to be what? Concave up. Don't worry, we didn't define it yet, but we will. You can't just say that. Okay, just we got to put a definition to this. But hey, what if the function's doing something like this?
Concave down.
Yep, concave down. Okay, come on, we got to define this. That's not good enough. It's pretty good though. Like a cup, concave up, right? Concave down like an upside down frown. True? Here. Concave down like an upside down frown, concave up like a cup. We'll remember that, true?
Mm-hmm.
Any function, that's where we go, oh, that thing's concave up, where's concave down, we can look and find it. But what's the definition? It has to do with the slope. So, everyone, if the slope